Okay, so hi everyone. Today we'll have Damiano with us, and he will give a talk about how to remove a trusted dealer in one round. Let's welcome the speaker.
Okay, so hi everybody. My name is Damiano, and I'm a PhD student from Aarhus University in Denmark. Today I will present our work, which was accepted at Eurocrypt this year, so it was already presented in May. And yeah, this talk will be kind of a whiteboard talk in the sense that there will be no actual slides. It's just me writing on my iPad. So the title is Distributed Correlation Samplers, How to Remove a Trusted Dealer in One Round. And it is the result of a collaboration between myself, Peter Scholl, and Sofia Jakubov, all from Aarhus University. Okay, what are the contributions? There are two main contributions, and the first one is the introduction of a new cryptographic primitive called distributed samplers. So basically, this consists of one-round protocols for the secure generation of SRSs. And yeah, in the paper, we first introduce the notion, defining its security properties, and then we explain how to build them for any CRS distribution using obfuscation and FHE. The second part of the paper is instead about public key PCFs. PCF stands for pseudo-random correlation function. And yeah, basically these are one-round protocols for the secure generation of large amounts of correlated randomness. And public key PCFs have a very nice property, namely that the total communication of this one-round protocol is sublinear in the size of the outputs. So the parties will just send one short message, and after that they will get all the correlation they need without further interaction. Okay, the notion of public key PCF wasn't new, actually. It was introduced in a Eurocrypt 2021 paper called The Rise of Palier. And here the authors designed public key PCF for two specific types of correlation, namely OT and vector OLE correlation. So restricted to the two-party case. In this paper, instead, the one that I'm presenting now, we first formalized the definition of public key PCF that was still to be done. And then we explain how to construct public key PCFs for any correlation using distributed samplers, so the first primitive I introduced, and obfuscation. Okay. The plan for today is to focus on distributed samplers. I will explain what they are and how to build them. And then if I have time, I will sketch how to build a public key PCF using distributed samplers. All right, so let's get started. I will sketch what a distributed sampler is. We work with n parties with dishonest majority. So up to n-1 of these are corrupted. We also work with static corruption, meaning that the subset of corrupted parties is chosen at the beginning and it is never changed afterwards. Our goal is to generate a sample R from a distribution D using only one round of interaction. So in our main application, namely generating CRSs for MPC protocols using one round, this distribution D is the one describing the CRS. Okay, so in distributed samplers, the party will speak all at once, will send only one message, and after that, everybody is able to derive a sample R from the distribution without learning anything else. In particular, the randomness used here by D is kept secret. So to give an example, D can be the distribution that generates a large RSA modulo. And yeah, the distributed sampler allows to generate one. Every party will have the same, using only one round, and without learning the factorization. Okay, so the syntax is the following. Each party PI will send the message UI. All the messages are sent simultaneously. And after that, everybody is able to derive the output by running a deterministic function called sample on the transcript, U1, UN. So here you can notice that an adversary that doesn't corrupt anybody is still able to retrieve the output. It just by just listening to the communications, it knows everything about, like, it can retrieve R. Okay, how do we define security? Well, it depends on the power of the adversary. So we consider two settings. The first one is against non-rushing semi-malicious adversaries, and the second one is against active adversaries. So a non-rushing semi-malicious adversary is like a semi-honest one in the sense that it has to follow the protocol, but at the beginning, it can also choose the randomness of the corrupted players as it likes. And this adversary will be non-rushing. So this choice of the randomness is made at the beginning of the protocol. So before the messages of the honest parties are delivered. Okay, in this first setting that is slightly stronger than semi-honest, a distributed sampler is defined as a one-round protocol that implements the following functionality, FD. So the functionality generates a sample R from D, and then it outputs R to all the parties. Okay. So in this setting, we obtain distributed samplers for any distribution D that is computable in polynomial time in the plane model. So we don't even need SRSs here. And based on polynomially secure obfuscation and polynomially secure multi-key FHC. So I will explain later what these two primitives are. Regarding polynomial security, it means that it's a standard definition of security, namely for every PPT adversary, the advantage in the relative security games is negligible. Okay, so moving to the active case, we need to modify the functionality. So this functionality is split into two phases. We denote it by FD active. In the first phase, the functionality interacts with the adversary. The latter queries for samples identified by labels ID, and the functionality replies by generating an element RID from the distribution, and it replies back to the adversary with the sample RID. So clearly, this querying procedure can be accessed as many times as the adversary wants. But in particular, a polynomial number of times because A is PPT. In the second phase, the adversary can specify one of these labels, ID hat, and the functionality outputs the corresponding value, R ID hat, to all the honest parties. Okay, now I would like to explain why we need this particular functionality. And the reason is rushing behavior. So when the adversary is active, it can first wait for the messages of the honest players, and then it can choose adaptively the messages of the corrupted parties. So suppose that these two players are corrupt. The adversary first waits for U1 and U2. And then it can rerun the distributed sampler in its head many times using U1 and U2, but regenerating UN and UI every time. In this way, it obtains many different samples. Then it can choose the one that it likes the most, and it can send the corresponding two messages in the protocol. And in this way, it is sure that the honest parties will output the value it chose. And yeah, this functionality here models exactly this behavior. First, the adversary gets a lot of samples, and then it chooses the one that it likes the most, and it forces the honest parties to output it. Anyway, I would also like to argue that this functionality is good enough for our main application, namely generating SRSs for MPC protocols. And the reason is the following. So, okay, MPC protocols sometimes have SRSs that are bad, namely SRSs for which security is not guaranteed. But the probability of sampling such SRSs using the distribution D is negligible. So here the same happens. Like the adversary can query for samples, but with overwhelming probability, none of the bad SRSs is produced. So in the end, RID hat will be also a good CRS, and the security of the protocol that uses the distributed sampler will be guaranteed. Okay, what did we obtain in the active setting? So we again built distributed samplers for any distribution D, but we had to move to the random oracle model. And in subsequent work, we proved that this is necessary. And our assumptions are more or less the same. So polynomially secure IO, polynomially secure multi-key FHE, and also NISIX, of course, polynomially secure ones. So the goal for today is to explain how to build distributed samplers in this setting, so in the non-Russian semi-malicious setting. I don't think I will have time to present the active construction, but I will just say that basically we built a compiler that compiles every one-round protocol with non-Russian semi-malicious security into a one-round protocol with security against active adversaries in the random oracle model. And this compiler maps this functionality here to the one on the right. And yeah. Basically, the technique are based to are the same as the universal sampler paper. It's a AsiaCrypt 2016 paper, if I remember well. Okay. Now I will explain how to build our distributed samplers, and I will proceed by attempts. So the first constructions will be broken, but gradually we will fix them until we reach to the actual solution. So let me take another color just to make clear what changes between the various attempts. So first attempt, and we call it multi-key FHE. Okay, so what is our goal? Our goal is to generate a sample R from a distribution D using only one round. So the first issue that we encounter is how to choose the randomness that is fed into D to generate the output R. So clearly this randomness has to be chosen jointly by the parties. So our solution is that every party PI takes a random string Ri. And what we feed into D is the XOR of R1, Rn. Clearly, we cannot compute this in plain because if we leak the RIs, there is no privacy. So the protocol is broken. So instead, we perform this operation in an encrypted way using multi-key FHE. So multi-key FHE is similar to standard FHE in the sense that we can homomorphically apply functions on ciphertext, but it has an additional property, namely that we can apply homomorphic operations even on ciphertext that are encrypted under different public keys. So it will be clearer now what I mean. So each party PI in the construction generates a fresh multi-key FHE keeper, so PKI, SKI, and then it encrypts its random string Ri under PKI. So here we have CI, encryption under PKI of Ri. And yeah, party PI will send to the other parties PKI and CI. So here we get PK2, C2, PK1, C1, PKN, CN. Okay, now we have n ciphertext encrypting then random strings. They are all encrypted under different public keys, but this doesn't matter. We are still able to evaluate the function D on homomorphically on the ciphertext. And so all the parties end up with the same encryption of the output R. So we denote it by capital C. And yeah, this is the output of the evaluation of D over C1, Cn. So now everybody has an encryption of the output. It's just a matter of decrypting it. But the issue is nobody can do this alone, because in multi-key FHE, the output of the evaluation is encrypted under a joint public key. So we can denote it by the concatenation of the n public keys. So in order to decrypt this C, the parties need to collaborate. In particular, each party PI needs to compute a partial decryption. We denote it by DI. And this is the output of a partial decryption algorithm that takes as input the secret key SKI and the ciphertext C, the encryption of the output. Party PI will broadcast DI. So here we get D2, D1, and DN. And after that, everybody is able to retrieve the output. They use an algorithm called the final decryption. It's deterministic, and it takes as input the n partial decryptions. So everybody can compute this. All right. So this construction allows to generate a sample R without leaking any information except R itself. The only issue is this is not a distributed sampler because it's a two-round construction. First, the parties send the public keys and the ciphertext, and in the second round, they send the partial decryptions. So a distributed sampler is a one-round construction, so we need to get rid of one of these two rounds. Clearly, the second one. So let me erase the things that we need to change. So no partial plain text that are sent. And yeah, this leads to the second attempt. Okay. And I will call it the evaluation programs. Okay. Now, the idea is the following. So each party PI, along with PKI and CI, sends some other information that will allow the other parties to retrieve the partial decryption DI of the ciphertext C here. Of course, this information will depend on the secret key SKI because it needs to leak the partial plaintext, but at the same time, it needs to hide SKI because otherwise the construction would be completely broken. So we need a very powerful primitive, and so we rely on obfuscation. So what is obfuscation? Obfuscation is this algorithm. It takes as input a circuit and it outputs another circuit that computes exactly the same function. But this output will be scrambled. So it's really hard to tell what the original circuit performed. We are still able to retrieve the outputs, but we have no idea how they are computed. Okay, so each party PI will now send a program, an obfuscated program, we denote it by EVPI, and it stands for evaluation program. So we get EVP2 from party P2, EVP1 from party P1, and EVPN from party PN. So what's the code of this program? Okay, I will sketch it here. So EVPI will have the secret key of party PI hard-coded, and also the corresponding public key and the ciphertext CI that is sent by PI in the protocol. The inputs to this program will be the public keys and the ciphertext of all the other parties. And yeah, first of all, EVPI derives the encryption of the output C by evaluating D over the N ciphertext, the one given as the input and the one hard-coded. And then EVPI performs the partial decryption using the secret key that is hard-coded. And the output will be DI. Okay, of course, this program is obfuscated, so one can hope that the secret key here remains hidden. So we just obtain DI without understanding what operations are performed. This construction allows the parties to retrieve the output R using only one round. In order to do that, all they need to do is they take the evaluation program of party PI, they feed it with the public keys and the ciphertext of the other parties. This program will output DI, And since this operation can be performed for FDI, the parties will have then partial plain text. And at that point, everybody can run the final decryption locally and retrieve the output. The question is security. And actually, this construction is broken. And there are two main reasons. And the first one is a consequence of the residual function attack, which is a common issue to all one-round MPC protocols with private inputs. Here, actually, we have no private inputs because our goal is to generate a sample R from the distribution D. But in the construction, this Ri kind of acts like a private input. And the reason is PI always use the same Ri independently of what the other parties send. And this leads to an attack. In particular, the adversary, after the execution of the protocol, can rerun the distributed sampler in its head many times, fixing this method. So always using the same methods for party PI. For each of these executions, the adversary obtains a different output. And these outputs are all correlated because they all use Ri as share of the randomness for party PI. So depending on D, this can completely leak Ri, and so the protocol is completely broken. The second issue is subtler, and actually it's not completely an issue, it's just something that we don't really like. So the security of the protocol would rely on the fact that Ri remains secret as long as PI is honest. But in the protocol, we send an encryption CI of Ri. So in the security proof, we need to rely on semantic security. And semantic security holds as long as the secret key SKI is not leaked, or we leak no information about it. And here, actually, this is not the case because the secret key is hard-coded in EVPI. One can say, okay, the program is obfuscated, so there is no way to reconstruct SKI. But we need to argue this formally. So in the security proof, we will need to substitute EVPI with another program that is indistinguishable. But this second program shouldn't contain the secret key hard-coded, and so it will simulate the partial decryptions instead of computing them. There is a way to obtain this program, but to prove security, we would need an exponential number of hybrids. And that's because we would need to modify the behavior of the evaluation program for all its inputs. And the number of possible inputs is exponential. For each of these inputs, we need to switch from the partial decryption to its simulation. And yeah, if we have an exponential number of hybrids, it means that we need to rely on sub-exponentially secure primitives. That means primitives that are for which the advantage of the adversary is less than negligible. It's 1/2 to the lambda to the epsilon for some epsilon between 0 and 1. And it's a stronger assumption. We would like to avoid this. So this leads to the third attempt. So I will erase what is not needed anymore. So yeah, let's maybe wait a second. So third attempt, the key generation programs. All right. So what is the goal now? This is actually the trickiest part of the construction. So we would like to obtain a construction in which PI uses a different random string Ri and a different key pair for every choice of the messages of the other parties. So I explain it in another way. So we would like that if any of the other parties changes its own message, then in any execution, either the real one or one in the head of the adversary, PI uses an independent looking random string Ri and an independent looking key pair, PKI, SKI. So it sounds like something impossible, but there is a way to obtain this. And the solution is not to send PKI and CI directly to the other parties. We instead send an obfuscated program that takes care of the generation of the randomness and the keeper. So let me erase a bit the things that are here, and then I will explain the details of this program. So each party will send one of these programs. So KGPI stands for a key generation program. So the code will be the following. So KGPI will have a functional PRF key KI hard-coded, and it will take as input the key generation programs of all the other parties. Actually, here there is an issue, but for the moment we ignore it. We will deal with it later. So the first operation performed by this program is to feed the inputs into a punctuable PRF. So the key will be KI, and the input KGPJ, J different from 1. And in this way, the program obtains two pseudo-random strings, Ri, what we will feed into D as a share of the randomness, and Ri prime. This Ri prime will be used to generate a fresh multi-key FHC keeper. So PKI SKI will be the output of the multi-key FHC key generation on input randomness Ri prime. And finally, the program encrypts Ri, the share of the randomness, under the public key we just produced. Encryption under PKI of Ri. And the output will be the pair PKI CI. What do we notice here? We notice that if any of the other parties changes its own key generation program, then the input to the PRF changes. And so we obtain independent looking random strings. And for the same reason, we obtain an independent looking keeper. So this is exactly what we want. So now if the adversary retries the attack that I described before, so it can rerun the protocol in its head many times, changing the messages of the other parties, but using the same key generation program for party PI. But yeah, by changing any of these other programs, the output will use a different random string that looks independent of the previous one. Basically, all the outputs the adversary derives will look independent. Okay, since I changed the way we generate the public keys and the ciphertext, I need to modify also the evaluation program a little bit, but the ideas are the same as before. So now we hard code the punctuable PRF key KI and also the key generation program of party PI. So this evaluation program will be way bigger than the key generation programs. The inputs will be the key generation programs of the other parties. So the evaluation program will still derive an encryption C of the output using the homomorphic properties, and then it will perform the partial decryption. But first of all, we need to derive the ciphertext and the public keys of the other parties. And how can we do this? Well, we are given as input the key generation programs of the other parties. So we can simply run them inside the code of EVPI. So for every J, EVPI will obtain PKJ CJ by running the key generation program of part PJ on input the other key generation programs. And then we also need to derive the secret key SKI. And we can do this in the same way as above because we have the puncturable PRF key Ki. So first we derive Ri prime by running the PRF on input KGPI. I different from KGPJ for J different from I. And then we use Ri prime to generate the secret key. And it will be the same as above, clearly. And yeah, at that point, we perform the same operations as before. Okay, so in this construction, the parties are able to derive an encryption, the output using only one round. The idea is the same as before. Everybody takes the evaluation programs, they feed them with the key generation programs of the other parties. They obtain the n partial decryptions, and everybody runs locally the final decryption. Security can be proven if it wasn't for one little detail.
Sorry, I have a question. So here you don't need to share the EVP, right? You only need to share the key generation programs to everyone.
No, we also send the evaluation programs. We send both of them.
Okay, but like if you send it, then where is it used?
Sorry?
If you send it the evaluation program, then where is it used?
The evaluation program is used to obtain the partial decryption. So everybody takes the evaluation program of EVPI, and the parties feed the key generation programs of the other parties. And the key generation programs of the other parties will be run inside the code of EVPI. And it will, and in the end, the evaluation program EVPI will output the partial decryption DI.
So do I need other people's evaluation program?
I need the other people evaluation program because I need to derive the public keys and the ciphertext of the other parties so that I can recompute the encryption of the output.
But that depends on the key generation program, right?
Yes. So I'm confused. So what is the question?
So the question is, do I need to obtain other people's evaluation program?
I need the other people evaluation programs because that evaluation program, the one of the other people, will give the partial decryption of the other people.
Oh, I see. Okay.
So yes, the evaluation program EVPI doesn't need the evaluation programs of the other parties. But in order to retrieve DJ for J different from I, we need EVPJ.
Okay, I see. Got it. Thanks.
Okay. So using this strategy, everybody obtains the n partial decryptions. So then we can run the final decryption locally and reconstruct the output. So as I was saying, regarding security, we can prove it if it wasn't for one little detail, namely that the key generation program, as you see it on your screen, doesn't exist. And that's because KGPI is a circuit, and it takes as input n-1 circuits that are exactly as big as the circuit itself. So basically, the inputs don't fit into the program. And yeah, the solution to this problem is to use a hash function. So instead of providing KGPI with the key generation programs of the other parties, we provide it with a digest. And yeah, we input the digest into the PRF. And yeah, the security properties will be the same. So if any of the other parties changes its own key generation program, under collision resistance, the digest changes, and so the input to the PRF changes. We obtain two independent looking random strings, and so an independent looking key pair. Yeah, of course, I need to add a hash function even down here. So in particular, the input to the PRF will be hashed, and also to these key generation programs, but still we give the full programs to the evaluation program because we need to evaluate them inside the code of VPI. After this modification, we obtain a working distributed sampler that is secure. And yeah, this is the final solution. Before moving on to public key PCFs, I would also like to explain why we can prove security without relying on sub-exponentially secure primitives. And the reason is that in order to argue security in the protocol execution, it is sufficient to hide the secret key used in that particular execution. And that means that we just need to modify one specific executions of these two programs. In particular, it is sufficient to puncture the PRF key KI in the right position, and all the information about the actual execution of the protocol can be removed. And the reason why the simulator will know where to puncture this PRF key is because we are looking for security against non-Russian adversaries. So the simulator will receive the randomness chosen by the adversary at the beginning, and only at that point it will generate the messages of the honest parties. Okay, this is all I wanted to say about distributed samplers. So now I would move on to public key PCFs. So we still work with N parties and with dishonest majority and static corruption. But our goal now is a little bit different. So we don't deal with a distribution D, but with a correlation function C. So this is a function, a randomized algorithm, taking as input the security parameter, and it has N outputs, one for each party. In particular, we denote the ith one of these outputs by Ri. So these values are all random, but they are also correlated. For instance, they can be shares of Bieder triples. So additive shares of A, B, and C, where C is the product of A and B. In a public key PCF, each party PI will send a small public key. So this is not a multi-key FHC public key, but it's a public key for the public key PCF, of course. Yeah, everybody will have also a secret key. And after this only round of interaction, everybody can expand the public keys, obtaining large amounts of correlated randomness without further interacting. And the expansion of these public keys takes place as for a PRF. So there will be a NaN space denoted by capital X. And for each element in this NaN space, party PI can derive a random correlated values RIX, which is the output of the PCF evaluation on input, then public keys, the secret key of party PI, and the nonce X. By performing this operation with their own secret key, also the other parties will obtain a correlated value. Like here it will be R2X, here it will be R1X, and RNX. And these N values, all derived from the same nonce X, will satisfy the correlation rule here in the middle. Okay, now I will explain how we can build these public key PCFs using the distributed samplers. I will start from a construction in which we allow SRS, and then the idea is to use a distributed sampler to get rid of this CRS. Okay. In the scheme, we rely on a public key encryption construction. So each party PI will send its own public key for this public key encryption scheme. Yeah, of course, there are also the secret keys. The CRS will consist of an obfuscated program. So it will have a puncturable PRF key hard-coded, and it will take as input n public keys and a nonce x. So here x belongs to the nonce space of the public key PCF. So the obfuscated program will first run the PRF with key k on the inputs. And it will derive a pseudo-random string R. Then it feeds this R into the correlation function C. So we will obtain the n correlated values R1, Rn. And finally, for every I, we encrypt the ith one of these outputs under the ith public key that is given as input. So Ci will be the encryption under PKI of Ri. And the outputs will be C1, Cn. Okay, so this trivially leads to a public key PCF. All the parties need to do is to run this obfuscated program on input the public keys they sent in the only round and the nonce x. The output will be the encryption of these correlated values, but only party PI will be able to decrypt the ith one of this ciphertext and retrieve Ri. Now, how can we get rid of this CRS? Well, we use a distributed sampler. In particular, its party PI along with PKI will send a distributed sampler message UI for the distribution that generates this CRS, this obfuscated program. And yeah, by running the distributed sampler, everybody ends up with the same obfuscated program and no information about it is revealed. So in particular, this PRF key K remains secret. So furthermore, the size of these messages will be logarithmic in the total size of the nonce space. So the messages will be small. And just remember that the size of the nonce space is essentially the number of correlated material that we can generate. Okay, so in the paper, we presented many public key PCF constructions. Some of them have active security. Some of them have only semi-malicious security. Some of them use the random oracle, some of them don't. Some of them use polynomially secure primitives. Some of them need sub-exponentially secure primitives. But the gist is always the same. We always rely on this trick. And yeah, this is more or less all I wanted to say for the seminar. So if there are any questions, I'm happy to answer.
Okay, are there any questions here in the audience? Okay, doesn't look like it. Then thank you so much for your talk.
Okay, perfect. Bye.
Bye.